Today we'll take about thermochemistry, and this is just a simple concept. When you go 12, you will have more in depth about the thermochemistry or thermodynamics. So thermochemistry will take just a small tiny concept. It's not really in depth, but at least you will have. So we have to know that we have two types of energy, potential and kinetic. So all the time the energy is made of potential energy and kinetic energy, and they're interrelated to each other. They're converted, one for kinetic can be converted to potential, potential can be to kinetic, and so and vice versa. For example, if I have a marker here, this marker is at rest, it's not moving. So it does not have any kinetic. Kinetic is always related to motion. And kinetic energy, half of the mass multiplied by velocity square. But this is, I did not put here even the formula, but at least you will know. 12, you'll have more in depth. Half of the mass of this multiplied by velocity square. How about the velocity? The velocity means speed. It's not moving, 0. So no kinetic energy. How about potential? Yes. So if I relate myself, the height from here to the ground, there is a distance, correct? And it has a mass. The subject has a mass. It's at distance from the ground, and there is gravity, correct? So mass multiplied by the gravity multiplied by the distance or the height is called potential energy. Now, if I let it go, it will start moving. So the potential energy being now converted into what? Into motion, into kinetic energy. So it will go all the way until it hits the ground. Then all the potential energy totally converted into kinetic. Correct? So mgh, let me write it for you. So kinetic energy, potential energy here, just E bar mass multiplied by the Earth gravity multiplied by the height or the distance, the location from this object. So the E kinetic, half of the mass multiplied by velocity square. Correct? Now, when it hits the ground, kinetic energy is gone because it's at rest. Correct? So then the whole kinetic energy will be 0, and the potential energy is 0 because there is no distance. Correct? The distance is 0. However, now both of them are converted into what? Into work. So here it is. Kinetic energy is 0. Potential energy is at the maximum. Goes down. Potential energy is decreased. Kinetic energy is taking now place, increasing until it hits the ground. So the kinetic energy is hitting the ground. Velocity stops, 0. The height is 0. So whereas the energy? Energy does not die. Energy does not die. So this is converted into work. How? Because if I let this one on my foot, I feel the pain, right? The pain is coming from the energy itself. So the pain is converted, the energy is converted into work. Work, I can feel the pain on my foot. So if you have a rock, let it go, rock at the top of the mountain, kinetic energy is 0 because there is not moving anywhere. Kinetic means start moving, is throw it, start moving until it hits the head of somebody. Then kinetic and the potential is converted into work, and thus you can feel the impact of the work on the head of that person, correct? So now, if you look at this, if I have this one here, let me get this one here, just this is, as you will see, we'll cover this one later on, but at least the thermodynamics, that's a 12 subject. We have two laws. First law of thermodynamics, second law of thermodynamics. The first law of thermodynamics, that's the internal energy of any object. Internal energy is made of the heat and work together, combination of both. So if you look at this, let me allow me to get out of sharing and then share the this one here. So this is the first law of thermodynamics. I don't think that I will put any question about this. This more or less is 12 more in depth, but at least we know if we'll take this one here later on as we look at the enthalpy. So internal energy, U equal Q is the heat multiplied by the work, correct? Now, this is the first law of thermodynamics. The second law, we did not take it, you'll take it in 12, but at least you know, if you go for the second law, you will know that the second law is you cannot produce an engine that works for infinite time. I mean, it cannot be working forever. So, and therefore, it has to stop. It has to come to the end. And therefore, you will see that's predicting even the end of the whole universe. So it looks like the disorder of universe is increasing to the point that it will collapse. That's what it says. So if you look at the thermodynamic number two is more or less, here it is. Cannot just produce an engine or produce anything without consequence, and it has to start, it has an end. And therefore, even the universe, one day it will end. Correct? So that's what it says. So an entropy, that is disorder of the matter, world will increase and never decrease. So always increase the disorder, disorganization of the universe. A lot of stars, meteoroids, a lot of black holes inside the universe. So it's a lot of disorder or organization. It will come to the point the whole thing will collapse. This is topic you will be taken more in the 12, but at least I give you just the sense of it. I'll stop sharing. I'll share our PowerPoint here. Okay, so, and that's what it says. So here it is. And we have two types of thermal energy, or two types of thermochemical reaction, thermal energy or thermochemical reaction. Now, you know that we talked about these types of chemical reaction, correct? We have single, double replacement, single replacement. We have decomposition. We have synthesis or combination. We have combustion. Then we said we have redox reaction, which is coming out of those single, can be single and combination or synthesis, decomposition, and all those are redox reactions. Now there are some types of reaction for thermochemical reaction. Thermochemical reaction, you have to specify when you write this thermochemical reaction with its chemical equation. So you have to specify the heat. If the heat is written on the right side of the chemical chemical equation, this is called an exothermic. So the reaction comes together, but the heat will be given off. If the heat is written at the reactant side, to the left side, this is called what? Endo reaction, endothermochemical reaction. And this is those two here. So, and you can see this, the curve here. By the way, that was one of the ACS exam long time ago. Give it the curve, and then you have to, and then give you multiple choices. So out of this curve, whenever the product is down, lower than the reactant, so here it is, guys. Just take a pen here. Reactance is lower than the products. You see here, it's lower, correct? This is an exothermic reaction. Energy is, or heat, energy, heat is energy. It's given off, it's given off. So this is an exothermic. So what we have to learn about this? Well, it turns out to be, there are two heats or two energies we have to be concerned of. So one called, this called activation energy. And this called here, the activation energy. This called here what? Activation energy here. And the distance between reactant and product energies are called reaction energy, correct? Chemical reaction energy. So chemical reaction energy, the difference between or formation energy or chemical reaction energy. So what means by activation energy? Activation energy is energy needed, correct? Needed by the reaction to let it start. So you cannot start any chemical reaction unless you satisfy the amount of activation energy being present, correct? So now if you look at this, for example, look at this here. If you ignite, if you have your car, in your car combustion reaction, you have gasoline and you have oxygen, air. Put them together, nothing will happen. You have to ignite through the spark plugs and put the ignition point of the gasoline, so the reaction will come, and then you have a combustion reaction of gasoline and oxygen and air. Before, no spark plugs, there will be no reaction. So if you want to keep your car dead or somebody's car's dead, just pull the spark plugs. The car cannot move by all means, because there is no energy to move the car, correct? The pistons up and down, it's not coming up and down because there is no energy is driving the pistons up and down and moving the car forward, correct? So that's the activation energy needed to start a chemical reaction. Without it, so in our case, the car case, you need spark plugs. Spark plugs give you ignition sparks, which is enough energy to get those those reaction between gasoline and oxygen in progress. The formation or reaction, chemical reaction energy or enthalpies, those are called what? Those are the difference between products minus the reactant. We'll come back and look at them. What's striking is of those, you can see that exothermic has the least activation energy. So what's unique about this, the activation energy is small in the exothermic. The activation energy in endothermic is very large. Can you see that? And the products minus the reactants, this reaction, heat of the reaction between there's a difference between product and reactant. This is still product against minus the reactants. But the unique about those two, the products is up. Here the products is down. Activation energy is very high. Activation energy is down. So the activation energy is lower. So that's the difference between exothermic and endothermic. So, and exothermic is used as an example in hot pack, and the endothermic in cold pack or ice pack and hot pack. So you can use them. You can see an example of those in the real life. So we just take this one here out. Here's an example. If I have the heat, if I have the heat at the product side, then I'm dealing with exothermic, correct? If I'm dealing with the heat at the left side, this is an endothermic. So another way we can express this one here, the heat is sometimes recognized. It is, guys. Heat is recognized by enthalpy. It's the same thing, heat. This is at the right or negative value. Negative value. And here delta H, heat at the is positive. Correct? This is positive, this is negative. So now you will ask yourself, do we have a negative energy? No. You'll get the Nobel Prize if you get the discovery of negative. Energy is always positive. There is no negative energy. There is only time that we don't know that we have negative energies when you are dealing with black hole inside the universe. Somewhere is we don't know what's happening. It looks like even the mass is converted. So the whole physical laws we know, maybe inside the black hole, because it's what is black hole? Somebody will tell us the black hole in the universe? Well, it turns out black hole, a huge, you don't know if it's star or not star, but it's a huge hole, looks like a black, is like a vacuum, works like a vacuum. Any object, any star, meteoroids, planet, any object near it will be sucked into it. It's like a vacuum universe of the universe. So whenever this huge thing here looks like a big star, huge star, so like a huge, even bigger than the sun, we know, and then anything near it, it will be sucked into it. What's happened inside this, we don't know. So there is a lot of unknown stuff happening inside. So there's a lot of, even the mass is converted and everything, and the energy is converted. So do we have a negative energy inside? We don't know. But energy is always positive. We put this one here because that's for us. The negative means given away, losing. So here it is, losing. The system, the chemical reaction, the system is losing energy. Here is plus gaining. That's the whole idea. Gain. So gaining. So the positive is gaining and the negative is losing. But energy is always positive. There's no negative energy at all. Okay, so heat, what is heat? Heat, as I told you, heat is energy. And we use the tool to measure this energy or heat by using temperature. So temperature is just a tool used to measure the energy, the heat. Heat is energy. So what is heat? Heat is really energy, correct? So, and the heat is measured in metric system in calories. Let me, you can see it here. Calories, CAL, small. Our international system, SI, is in joules. And the joule is, 1 calorie is, you have to memorize this for the final exam. I think they will give it to you, but I'm not sure. 1 calorie is 4.184 joules. So this is the relationship between metric and international system. Now there is another one. You'll see it in the literature, British Thermal Unit, BTU. This is unique in United Kingdom. Just the SI in our textbooks, in ebooks, the SI or the metric, calories or joules. So most of our heat or energy is coming from the sun. The sun is in charge of our heating our galaxy. And our galaxy is called the Milky Way galaxy. It's made of a lot of stars, not only the planets we know, but a lot of stars, meteoroids, called the Milky Way. And if sometimes you can see it very nice on the against the dawn, very dark before the sunrise. Sometimes you can see those bunch of called the Milky Way. So here is a definition of the heat capacity. What is heat capacity? Well, it turns out by definition, we define the heat capacity here, and you can make yourself a flash card or a piece of paper to write those formulas, because you need those formulas for future quiz. So heat capacity is this. It's equal to heat divided by temperature difference. The temperature difference is T final. You have a system. Start with T initial, that's T final, minus T initial. T initial. So you start with starting temperature, you'll end up with final temperature, and that's the difference. So the heat divided by this, by definition, called heat capacity. Now the heat capacity can be specific or molar. If we add to it C Q divided by mass delta T. Now we speak about this being now specific. Okay, so now this is specific, as you will see. If we can say C equal Q, you have to write yourself a formula sheet with the formula. Q divided by N, number of moles, delta T, is a molar heat capacity. Specific heat capacity. So we'll start with this. This is just a normal heat capacity, correct? Divide this one here related to the mass. Then you speak about specific heat capacity. You divide it by number of moles. This is moles here, guys. This is moles. This is moles here. You divide it by moles. This will be your molar heat capacity. So specific, molar, and just a normal heat capacity, correct? So again, defined by what? Defined by from the formula itself, correct? By the formula itself. So the heat capacity, amount of energy needed, correct? Being absorbed or released, whether it's exothermic or endothermic, for a temperature change of 1 degree or 1 Kelvin. So amount of energy. So I'm defining the definition from the formula itself. Amount of energy per 1 degree. Here, the specific amount of energy Q here needed to raise the temperature of 1 gram. This is 1 gram here. 1 gram, correct? And then the Q will be 1 calorie. So amount, the specific heat, Q over mass over delta T. And here is just number of moles. You define this one here by number of moles. Now, out of this here, this is the heat capacity, the specific heat capacity, the molar heat capacity. Those are what? Those are, believe it or not, those are extensive, correct? Extensive means they depend on the amount. So if you increase the amount, the heat capacity will increase. If you decrease the amount, the heat capacity will decrease. So they depend on the amount of the matter itself. And here just an example of, if you put 250 compared to 25 grams, you'll see the difference 10 times will increase because you have the amount. Now, some physical properties are intensive, correct? Such as density, whether you have 250 grams of the material or you have 25 grams of the material, the density of iron will be the same. That's intensive, I-N-T-E-N-S-I-V-E. Extensive, on the other hand, sensitive for the amount. And those physical properties such as volume, correct, such as heat capacity, those are very extensive, very sensitive to the amount. So their value changing with the amount. So now this is what I said, the specific heat. We include the mass, correct? Specific heat capacity, correct? And this is the same thing here. Specific heat is defined amount of energy needed to raise the temperature of 1 gram of a matter 1 degree. Amount of heat needed to raise the amount of 1 gram 1 degree Celsius or 1 Kelvin. Now we have the molar, will come the molar. So if you replace M with N, number of moles, will be the same thing. Just instead of 1 gram will be 1 mole. To raise the temperature of 1 mole of the matter 1 degree. So, and here just an example, specific heat of 100 grams of aluminum is about 10 grams. So here it is. This is the amount here in calories and this amount in joules. Remember, 1 calorie, just to make this one here somewhere. So 4.184 joules. Joule is the scientist's name, so we honor him, Joules. Sorry, we honor Joules. So Joules is the S-I-S-J capital. So Joules. So just use the J, capital J. So here's an example of some of the heat capacity here. Specific heat capacity. And you can see somebody can visualize the heat capacity just visualizing it without the definition. I mean, C equal Q divided by the mass over delta T. Well, it turns out to be, if you look at the heat, all the heat capacity is the ability of a matter to retain heat. If you have a metal, you heat it on your furnace or on your stove, and put the metal away, it will cool down quickly or it will take longer time. What do you think? It will cool down quickly, correct? So the specific heat of metals, that's the lowest. Always specific heat or heat capacity, whatever you call it, or molar heat capacity, those are smaller amount. The ability to retain heat for the solids, the metals, solids, is very low. And you can see, can you see this one here, guys? Look at the values here. What is telling us? See here how small this one here, piece of wood, but look at the metals here, the solids. All those are very low. Now, if you go the liquids, they retain heat more. If you go for the gases, even more and more and more. We heat our houses using natural gas, correct? Can we use copper pipes to heat our houses? Can we? No, because copper cannot retain the heat that much. And copper has, I think here, look at this heat capacity here. Very low, 0.385, 0.385, correct? And this is joule per gram centigrade Celsius. So you cannot heat your house with the copper pipes. You cannot even heat with the steam, H2O. You have to have a gas because you can see that the solid, they don't retain the heat. They tend to be cooled down quickly. And the liquid intermediate and the gases, they retain the heat for a longer time. And that's because they're atoms all the way spread out all over the places, correct? Solid is one packed area, so therefore they can give the heat at once because everything is in one spot. Okay, so the ability to retain heat is really the heat capacity or specific heat capacity or the molar heat capacity. And you can see the elements and especially the solids, they have very low. Liquids, intermediate, gases are the highest. So we are heating our places using gases, natural gas, methane, propane, any gas that's not toxic, we can use it to heat our houses. So, but not metals. So let's look at this. Here I talked about this, the molar, correct? I replaced the M, the mass, with the number of moles is the same thing, correct? Just instead of the 1 gram of the matter, this is just 1 mole of the matter. See the definition here? Look at the definition here. 1 mole, we said. There we said what? 1 gram of the matter, 1 degree. Here is just 1 mole, correct? So, and instead of the units will be in gram centigrade Celsius, will be mole centigrade Celsius. So, but most of the time in the literature is the heat is this one here. This is the formula, you can pay attention for it. Out of this, I can have two sub-formulas. So what are those two formulas? Well, Q, the heat itself, is mass, correct? Multiplied by specific heat, multiplied by delta T, final minus initial, delta T. Correct? And the other one is mass equal to, as you see here, Q divided by C delta T. So out of one formula, I have two sub-formulas I can use. So out of one formula, I can use it for two sub-formulas. And you can see here, one of these sub-formulas is the mass. I can calculate the mass, correct? So here it is. You'll have it in the recording, but at least you know this, you have two sub-formulas. Now, calculate the mass. It says for us, we have to calculate the mass. And the mass is here from the sub-formula. That's the main formula. That's the main. That's the main. That's the main here. That's the main one. So and this is the sub-formula. We need the mass. Well, we need the heat. The heat is given to us in kilojoules, correct? And when its temperature decreases from this to this. So this is the initial. And this is the final, correct? So then you have all this one here, kilojoules. So the mass will be, you have to, because it's kilo and you are using grams, so it has to be, the kilo has to be transferred into just joules by multiplying it by 1,000. Kilojoules, you multiply this one here by 1,000 to transfer it into joules, because you don't need the kilo, because your specific heat always given. What's the unit of specific heat? Is joules per gram here, and centigrade Celsius. So joule per gram centigrade Celsius, or calories per gram centigrade Celsius. So you have to transfer, and that's what we applied here. We multiply this one by 1,000 to convert the kilojoules into joules, and then you divide it by the delta T. Delta T, the difference between them is 0, correct? And this one here is the H2O is 1 calorie, correct? H2O is a reference, and its specific heat is 1 calorie per gram centigrade Celsius. And this is equal to 4.184 joules. Right? So this one here, that's the joules here. You divide this one by the joules. Here is the division. The sign is division here. You divide joules and joules cancels out, and the gram will come up, and then centigrade to centigrade will cancels out. Correct? So now, what do you think about this type of reaction from 83.50 to 13.5? Is this cooling cooling the H2O is exothermic or endothermic? What do you think? What do you think? Exo or endo? If it's endo, you are putting temperature, and temperature will go high, correct? Because you are gaining heat, correct? So this is going from 83 to lower. So that's exo, correct? So means just by inspecting this is an exo process for H2O. H2O is losing heat. But if it's endo, you'll end up, you start 83, then you'll end up maybe 90, 95 degrees. So that's gaining the heat. Gain heat, then the delta T will be higher. So, okay, guys. Here's another example, heat calculations. C, that's the heat, that's the specific heat, that's the mass. The same thing we did. But here you have to, we are looking for the Q. Remember the two formulas we said, the two sub-formulas? So Q is mass multiplied by specific heat multiplied by delta T. You plug there in, you have to watch for the units. This is kilojoules, so your answer will be in kilojoules. How much heat in kilojoules? So your answer will be, whatever you get in joules has been converted into, so it asks you for kilojoules, correct? You have to watch for this. Your answer in joules, because specific heat of is given to you is calories or joules per gram centigrade Celsius. So you get joules. You divide it by 1,000. You get this, and you have to watch for what? For the sig fix. You have to watch for the sig fix. So the temperature is here. You look at this, make a difference out of them. I mean, when you subtract, then you can see that you have 3 sig fix coming out of the subtract, 1 digit after the decimal. So it will be 3 sig fix, and your answer will be 3 sig fix. Although you started with 4 here, but here the difference between them will be, if you look at this, will be 1 digit after the decimal, but the whole thing will be 3 sig fix coming out of this. Subtraction will be 1 digit after the decimal, but the whole thing then when you multiply, look at the 3 sig fix coming out. So you have 3 sig fix coming out of this. So here is the same thing here. It's asking for the mass. Look at the sub formula we did. You just play with this formula here with its 2 sub formulas back and forth to get the whatever is asked for you. Any question, guys? Any question? Okay, so here's this same thing here. So mercury is heated from 25 to 155. Now, what is this, endothermic or exothermic? You are putting heat into the system, correct? Your system is mercury. Your system is made of mercury. Mercury is a metal, liquid metal. That's the unique stuff about mercury. It's a metal, but liquid. It comes as a liquid. So this is an endothermic because you are putting heat into the mercury to heat it. So that's an endothermic. So from there, you can tell from the temperature, you can tell you are from 25 to 155. Correct? That's not even the melting point or the boiling point of mercury is higher than this. But at least you can tell this is an endothermic process for mercury because you are putting heat into and absorbs because it's Endothermic means always you keep the keyword here. Look, whenever you have this in your online assignment or in your quiz, the word absorbs means all the time what? Somebody will tell me? Means an endothermic. Means the heat has to be taken in. This is an endothermic. I did not look even at the word endothermic. I looked at the values here. And this is really true. It comes from 25, from smaller to higher. So I put heat. So the heat's absorbed. So this is an endothermic. So you can know it from the numbers. Increase, that's you have to put heat into the system. The keyword absorbs means what? Taken in. In order to heat it to 155, mercury has to take in heat. Right? So, and the other word here, just stick to, the other word is given off. So given off. So whenever you get in the exam or quiz or online, this is whoops. This is exothermic. This is an exothermic. So this is the TQ, the two keywords always used when it comes to heat. Heat absorbed in means endo. Heat is given off. That's an exo. So those are the two keywords I use. So we take this one out and then look at the now. Give you the mass is given to you. Delta T is given to you. Correct? It's endothermic, but we are not interested in the sign of it. Just we are interested specific heat always positive. So don't worry about the negative or positive. It's always positive, correct? So the mass is there. So what is asked for? Calculate the specific heat. Well, specific heat is Q over M delta T. Q is given to you. Where is it? This is Q. That's your Q here, correct? That's the mass. Everything is very nice. So mass is here, and this is your delta T. The difference between 155 minus 25. That's your delta T. That's delta T. You just plug in all these values and you get this, the whole thing. Now, I can ask you, or sometimes in the final exam, they can ask you about T final. They will give you everything. They will give you specific heat, correct? They will give you Q. They give you the mass. And then here is the key. Instead of this T final, correct? Minus T initial. So what they will do for you, they'll give you the T initial, tell you to calculate this. Well, that's doable because this is given, mass is given, Q is given, and the specific heat is given. So you can just solve for the T final. This is always the ACS, one of the favorite questions in the ACS exam through the years, even for TOEFL. Give you something like this, and the T final always asks to see the students are aware of playing around with the formula. So this is straightforward, asking for specific heat. Here it is, guys. Look at this. Can you see it? It's T final. That's the question here I was talking about. Chloroform is initially at, that's the initial, that's here, that's given to you, correct? That's the initial. What is the final temperature? That's what I said. That's a very favorite questions. I mean, through the years. So what is the final temperature? The mass is given to you. It has to be given to you, correct? And the heat is given to you. You have just to convert this one here into kilo, means multiply by 1,000 into joules. And then specific heat is given to you. So this one here is given to you, correct? This one is given to you. This one is given to you. The mass is given to you, and delta T here, instead of writing delta T, you say T final minus T initial. Look at this. This is, we convert this one, the heat into 1000 joules divided by, this is divided by, then you have the masses here, specific heat is here. This is delta T, correct? So delta T is T final minus T initial. Initial is given to you 25 degrees, correct? So this is the amount here. So you add this one here to it, so you get the value is this here. So just watch out for this type of question. I want to trick the students by just, you know, you ask yourself, where is T final? I don't see it in the formula. Well, it's there in the formula, but you have to work it out in the way that's, you get all delta T, and then delta T is T final minus T initial. That's what you got here, 6.044 degrees. Then you have to add, take it the other side, you add it to 25. The answer is 31 degrees. Calorimetry. Calorimetry is a method used to measure the heat or energy. So if we have a chemical reactions, we can measure the heat of this chemical reaction. As I said, you have to know how much you will start with of material and how much you are getting out of this chemical reaction. And calorimetry is one of the methods used to determine how much heat you are getting, how much heat you are getting out of chemical reaction. So there are two major types of calorimeter. You don't have to memorize. This one will not come in the ACS exam, it will not come the quiz. But even my colleagues said, they told me why we have to add those. But at least the students, they know there are adiabatic calorimeter and reaction calorimeter. We don't deal with adiabatic that much. Adiabatic means the heat is not changed. Adiabatic, anytime I say adiabatic, there is no change in the heat. There is, it can be used in the normal life, correct? Somebody will tell me what hypo means. Hypo means lower. If somebody went to the North Pole and said, this somebody here, this person here is catching hypothermia. Hypothermia, what it means? Temperature of the body of that person is lower than the body temperature of the human. Temperature of human about 37 degrees Celsius or 98 Fahrenheit. So hypothermia means what? Lower than the body, your normal body temperature, lower than 37 centigrade Celsius. So this is hypothermia. If it comes to say, okay, so I have a project and we have a problem. This problem is causing us to have adiabatic condition. Then the person will know that your system does not change any heat, does not generate, does not take in, does not give away heat, does not. So those type of expression, you have to be aware. So adiabatic, hypo, so all this hyper or per, hyper what? Higher. Hypo, lower. Adiabatic, no change. So hyper is up. You eat too much sugar, get hyper, correct? So the blood pressure will be very high. So the child is very hyper, so higher blood pressure. Hypothermia, lower. And adiabatic means no change in the heat, correct? Heat means energy itself. But the most important stuff is this one here. Chemical, this one is very important. That's what will bring some stuff. Sometimes they bring ACS exam, but not every time. But at least we are dealing with chemical reactions. We put some chemicals inside those calorimeters and we observe the heat change, and then we calculate from the calorimeter the heat, correct? That's very important. So adiabatic, we don't deal with them because there is no change in the heat. We are not interested in them. Some of the adiabatic, and you can see here, mixing solutions, dilution, crystallization. So there is no change in the heat. Those adiabatic. But the chemical reaction calorimeters, there is heat involved. So there is a heat involved in this. So here just show you a setup of adiabatic calorimeter inside the lab. As I said, that will not come. So at least show you what to do. So the reaction calorimeters, you don't, as I said, this one here, I should not bring, it's not there, but at least there are 4 types, correct? Heat flow, heat balance, constant flux, power compensation. Those are the types of calorimeter you are not dealing with. The most important, however, is this one here. We might be doing some experiment with this foam cup calorimeter inside the lab. I have to check that. So this is called foam cup calorimeter. This is a very simple calorimeter. It does provide a very good data. It's not 100%, but within the error, I mean, 10% error, it's not bad. It's acceptable in the lab. So this is a thermometer. So what's happened is you have a calorimeter. So you have here this calorimeter here made of, this one here is the thermometer to measure the temperature. This is the same like a coffee cup, correct? So this one is mixing. Here is, you mix it. You don't have to do it, just you can mix it per hand. You can just move it per hand. Here is H2O. H2O, you know that's H2O here, initial. What is the initial of H2O, correct? Temperature of the temperature. So you have to measure first the initial temperature of H2O you're putting in. You know the amount you have to put in. So density of H2O is 1 gram per ml. So if you put 10 ml, it's 10 grams. If you put 20 ml, that's 10 grams. That's 20 grams. So the amount, the density of H2O is 1 gram per ml. So whatever is you are putting will be equal to the mass. So now, on the other hand, I have a hot plate somewhere here. So I have a hot plate. I have a hot plate here somewhere. This hot plate, I have a beaker. Inside the beaker, I'm heating what? A metal. Here is a metal. Correct? I know the mass of it. So thermometer, put the thermometer inside, another thermometer. Measure the temperature of the boiling H2O, which is the same temperature of the metal. It's inside. So I know the T initial of the metal. So here what I know inside, I know the mass of H2O. It's H2O. And I know it's T initial. I measure this one here for H2O, T initial. Correct? Now I set up this one here. After knowing, I take this the metal, after reading the temperature, and quickly here take the lid out and put the metal. The metal is here. Keep it for until temperature, because it's hot, the metal is hot. The H2O is at room temperature, at lab temperature, 25 degrees, for example. So the temperature, because the metal is hot, heat always goes one way, from hot to cold. It does not go from cold to hot. If you have an ice block here, does it heat the room? No. Does it? No. Ice will heat the room? No. But heat, if you have a heater here, will heat all the stuff. So it goes from, the room is cold and you have a heater, so the heater will go from hot to whatever. So it's always transfer one way. So the metal is heating the H2O couple degrees, and then the whole thing will remain constant at temperature called T final. So this is, we get out of this reading here, T final for both systems. For the H2O and the metal, they are now in equilibrium, correct? So we keep them This is this lab. I'm not sure if we have it this semester or not, but we are doing it in the past. It's very nice, so you can see how the whole thing is. You are measuring the heat of the whole thing. So now we set up the whole thing here. Let me take the whole thing out. Here it is, guys. See here? And now, heat lost by the metal, because we have at the equilibrium, heat of the metal plus heat of the H2O will be 0, because they come to what? Correct? They come to equilibrium. When you dump a hot metal inside H2O at room temperature, so you come up, the heat is 0, correct? So then what will happen is you work on this a little bit. So the heat lost by the metal is gained by what? This is heat lost by the metal, is gained by H2O, correct? You can put the negatives here because I told you Q metal, correct, plus Q of H2O at equilibrium. When the whole thing is done, then the heat is 0. There is no heat coming out. Everything at equilibrium, there's no change. So when you put this one here 0, so this one will go out the other side with negative. So it will be negative here. So see the negative here coming from. So now you plug in all this one here together. Now from the experiment we have, you have the mass of the metal. That's the heat. Remember, the heat is Q here. You see, Q is mass multiplied by specific heat multiplied by delta T. Right? So that's for the metal. So we have here mass of the metal, specific heat of the metal, delta T of the metal, equal mass of H2O, which is the same, the density is the same. So whatever the volume you have, the density is 1. So the volume equals the mass because the density is 1, multiplied specific heat of H2O, which is 1 calorie or 4.184 joules, gram per centigrade Celsius, delta T of H2O. Now you have to watch for delta T of H2O is different from delta T of what? Of the metal. The only in common is T final. Delta T is T final minus, we take this one out and let's look at this. So here it is, that's the mass. See here. It is, this is the mass of H2O. This is the specific heat of H2O. The whole idea is to determine the specific heat of the metal. At the end of the lab, I told you have this metal and calculate your percentage error, how close you are your work in the lab. So you have to calculate. This one is always asked. This one's what? Always asked. So specific heat, correct? Then this is the final. I mean, this is the, well, that's the initial. It came out to H2O was at room temperature 25. When you dump the metal, this is the final here, correct? So if you look at this, and this is the final, whatever is I just played with the negative, so don't worry. This is final minus initial. This is the initial here. This is the initial. This is the final. So this is the density. So it's number of grams of H2O, specific heat of H2O, a final minus initial. And therefore you can see this is the initial one. This is the initial of H2O. So you calculate it out, and the metal is come out to be. So, and you can expect your data is correct because a metal, they have very low values. Metals, they have very low. So capacity or molar heat capacity or heat capacity by itself, it has always for metals very small number. If you get very large, then you have an error. Your intuition will tell you you have an error somewhere, correct? So intuition will tell you because it's a metal, you have to have a smaller value come out as a result. Inside, that's concerned the lab itself. So just here's another example. Give you H2O, correct? So here you have, instead of the metal, you can mix what? Other liquid with liquid. H2O with HCl, correct? That's heat of solution. Heat of solution or heat of dilution. You're diluting HCl with H2O or solution. So you have the HCl is 100 ml, and you have 100 grams of H2O, and then the temperature, the initial temperature of the HCl temperature of HCl is this, correct? And the H2O initially is this, and the temperature at both of them is because of dilution is exothermic, it's raised to 31, correct? So it started with, the HCl, the initial temperature of HCl is 46. Now, the temperature of HCl is higher, so it went out from 46 to final 32. That's an endothermic reaction in this case, correct? So what is this? So for H2O, temperature went from 24 to this. This is what indicating is energy was absorbed by H2O, correct? Energy is absorbed because you have to put energy, heat to raise the temperature. That's an endothermic. HCl goes all the way up and it decreases, so it has given the temperature, so it will be exothermic. Now, this is very important to the calculation here between both. So the mass of H2O multiplied by specific heat of H2O multiplied by delta T H2O equal to mass of HCl, correct? Or just this one here just for H2O, correct? So multiplied by specific heat multiplied by the final mass initial, correct? It says, what is the question? The question is calculate how much heat of H2O lost or gained, and you get this amount of H2O, correct? This amount of H2O. So you have the final is this, so it's positive. So the heat is gained, correct? This is positive. So you can see this is 280 kilojoules, correct? So I want you just to be aware of this calculation. Now, here's another trick. Give you the mass, and I need the final. Remember, the final is TF minus T initial, correct? So you have given to you the joules, correct? Absorbed by, what's the key of absorb, the keyword? Endo or exo? Endo. If it's given off, that's exo. Absorb means taken in. That's an endo. So the temperature is, what is the final temperature is absorbed by H2O at 25 degrees. So that's the initial one. Give you the initial one, correct? So now plug in the whole thing. This is the joules. Q equal to mass. This is mass of the H2O to 10 grams, 3 sig fix, multiplied by specific heat of H2O, 1 calorie or 4.184 joules per gram centigrade Celsius. Now you have to watch delta T is T final minus T initial, this here. So you have this, correct? So it came out to be 21 degrees, 20.1 degrees. So 25 plus 21 degrees, if you work it out, that would be 45, 45.1 degrees. That's the final degrees, correct? Okay, so it looks like you have to put heat. You have to put heat to increase the heat of H2O from 25 to 45. That's an endothermic process. Endothermic process, because you have to put heat to heat it up. If it's releasing heat, it will be given off, correct? It is. Okay, guys. As I said, the 1212 has more difficult approach than this one here. So we have still 5 minutes, guys. Cool yourself down now. So a piece of a metal, you have the mass. Let's look at this. You have the mass heated to this and put in H2O initially at, this is the initial temperature of H2O. This is for the metal. Metal is weighing this, was heated to this. That is the temperature initially of the metal. So the metal and H2O were allowed to come to equilibrium temperature. Calculate this final temperature. Final temperature is TF, correct? But you can put it this way, the same thing we did. So mass of the metal is given to you. Specific heat of the metal is given, what if the specific heat, this one is given to you too. This one here is given to you. Delta T, you have to watch, is T final, the equilibrium one, minus, what's the temperature here? The initial of the element, the metal, 100 degrees, correct? And here the mass of H2O is given to you. Specific heat of H2O is 1 calorie per gram centigrade Celsius, or 4.184 joules per gram centigrade Celsius. And here you have to watch out. There will be your T final. That's where you are working out. Minus the initial of H2O was 23.7, 23.7. So just work it out. Everything is known. So the TF for both sides, work it out, and you can find your temperature final is here. It is, it's given to you here, is 6.73 centigrade Celsius. Well, here's the same thing. I mean, it's just we have a metal, so we have a metal piece. Then I'll let you go. So this is the metal piece here, correct? Of the metal or of the solid, correct? The whole volume is 100 mils, correct? And the temperature came out to be from this to this. How much heat is generated per gram potassium for this reaction? Assume the density of solution after the reaction is the density of H2O. The heat capacity of the reaction vessel is this, 1 calorie per gram centigrade, or 4.184 joules. So this is the same heat, specific heat of H2O. So you plug in all the stuff here, correct? Now you need just the specific heat of the whole solution, correct? So mass is given to you, specific heat is given to you, and assume the total temperature change and how much heat, what's the Q. So you just calculate, this is the final, this is the initial, and you get this amount of joules, correct? Now, this joules here, you have this amount of grams, correct? You divide it by the number of grams given to you at the beginning, you get this here. Now, if I need this heat per mole, what should I do? ask you calculate this heat here, this amount per mole. Come on, guys. What should I do? Transfer the grams here into moles. How I do this? I need to know what the formula of potassium nitrate. This is the formula of potassium nitrate. I need the molar mass. Right? I need the molar mass of this. With the help of the molar mass, I have the mass, I can transfer the grams into moles. Are you following me here? But this one is just give you the joules per grams, and usually is they are joule per mole. So we'll come back, and Wednesday, I hope we'll finish this chapter. We took a lot of time in chapter stoichiometry. That's the most difficult part. And most of our students through the history are missing that chapter in the SES exam. The most difficult part is the stoichiometry part. So we spend longer time. Get your formulas ready. Look at them. Look how they solve problems. I will see you then this Wednesday, and we'll finish that chapter. Chapter is small. It's not big. Chapter next. Spend some time on the other one. So thank you very much.